Mixing a damn thing.
Okay, can I start it?
Yeah.
So let us come back to Akari mission instead of SDP mission for a while. Alright, so my name is Yoshiki Toba, JSPS Fellow working at Kyoto University in Japan. So as you know, we now have excellent HSC data, image and catalog. But I think almost all talks related to the HSC so far are about Akari sources with HSC counterpart. In my talk, I'll focus on the remaining objects, say Akari sources without HSC counterpart. You may think that those objects are easily selected just by cross-matching with Akari wide catalog and HSC catalog. But this is not the case. We found that there are many fake cases that's really, say, painful to find a real case. But if we could discover those objects that are undetected even by the HSC, they would be very, very interesting populations, such as extremely density galaxies, or agents, or high-resistive objects. So let us hunt for treasures in our NP field. Alright, so let's get started. So first of all, let me briefly mention why do we care about obscure populations. So the importance of understanding the obscure AGNs has been well recognized in many aspects. For example, the obscure AGNs may play an important role in the framework of coevolution of galaxies and supermassive black holes. And also some authors have reported that clustering strength of obscure AGNs is much stronger than that of unobscure AGN, suggesting that obscure AGN may be a progenitor of moderately massive galaxy clusters in the local universe. Also, density population including Compton-thick AGNs with hydrogen current density with greater than 10 to 24 per square centimeter could contribute to the cosmic microwave background CXV, or not, cosmic X-ray background CXV. Anyway, so an important point here is that the majority of agent population is indeed obscured. So, understanding the complete census of agent activity requires the identification of both obscured and unobscured populations. In the context of major merger scenario, agent luminosity and hydrogen current density and white double one and double two color are correlated. This result could indicate that particularly obscure agent phase has very active growing phase supermassive black holes behind a large amount of gas and dust. And also, white double one and double two color may be good tracer for agent activity and dust obscuration. Alright, next I'll tell you about the dataset and sample selection to find Akari sources without HSC counterpart. In order to find Akari sources without HSC counterpart and also to investigate their physical properties, I compiled multi-wavelength dataset from the optical, near-infrared, mid-infrared, far-infrared, and sub-millimeter that are obtained from HSC, Flamingos, Spitzer, Akari, Percher, and Scuba 2. We selected the candidates of Akari sources without HSC counterpart by using HSC, Flamingos, and Spitzer Akari images. For them, I investigate their physical properties by using those old dataset from the optical to sub-millimeter. So this is an example of the sample selection to find Akari sources without HSC counterpart. Original sample was drawn from Nagi-san's catalog, and she cross-identified with Akari NB-wide catalog with HSC band-merged catalog, and then picked up Akari sources without HSC counterpart in the catalog phase. However, as I mentioned at the beginning, many objects in this catalog are not always our desired objects. So then, I did a visual inspection to remove fake cases I mean, Akari sources really does not have HSC counterpart. I made a cutout images for all objects and then pick up a real case. This is an example of cutout images from HSC optical band, and also Flamingo's near-infrared band, the Akari near-infrared, mid-to-infrared short, and mid-to-infrared long band. And this white cross represents the position of Akari source. Alright, I did this kind of visual inspection for roughly 7,000 sources.
Of the 139 that you found, do they often look in Akari near-infrared spatially extended? That one did not look like point source.
Right, yes, basically some of them are detected only by an Akari near-infrared band, but some of them are detected by only mid-to-infrared short, either mid-to-infrared long, but they are basically looks like sort of extended shape.
Okay.
Anyway, so eventually 139 objects were selected as Akari sources without HSC counterpart in this work. Alright, let me move on to the results and discussions. In this session, we will discuss the following 3 topics. Okay? So this figure shows a histogram of Spitzer channel 1 and channel 2 color, I mean 3.6 minus 4.6 micron color. Red, black line is Akari sources with HSC counterpart, provided by Sonjin and Nagisa. And red shaded region represents Akari sources without HSC counterpart, I mean our sample. As you can see, Spitzer color of our sample is systematically redder than that of HSC Akari sources. According to the simulation I presented before, agent luminosity and obscuration, if we look at white W1 and W2, this color gets redder once agent luminosity and obscuration are increased. This part. So, this result could indicate that Akari sources without HSC counterpart may be red or dusty galaxies or agents. This is one implication from this test. Speaking of dusty population, submillimeter galaxies, obscure AGNs, or ultraluminous infrared galaxies may be representative of dusty population. So I tried to explain the SED of Akari sources without HSC counterpart by using typical SED template of dusty population. This figure shows the SED of an object, this object, and SED template as a function redshift for dusty SMGs, obscure AGNs, and up to 20 are overplotted. So data points are same in these 3 figures, and SED templates are different. If we look at far infrared of submillimeter regime, this object may be explained by those templates at redshift around 1, 2, 3, and 4. However, if we look at optical regime, this region, optical regime, any SED template cannot explain their observed SED. They need more dust extinction to explain the observed SED for our sources.
So more dust extinction even than R220.
Right. Okay. That's an interesting point, yes. Right. So what we learn from this kind of test is that, first of all, Akari sources without HSC counterpart may be located at redshift 1, 2, 4, and also they may be extremely dusty population whose optical SED cannot explained by typical template of dusty population. Alright, in order, let me discuss their physical quantities more quantitatively. In order to do that, I performed SED fitting with cigar. So as already many speakers, at least Tina, introduced what cigar is. Cigar is a very excellent SCD fitting board by taking into account energy balance between the optical part and infrared part. For Akari sources with HSC counterpart, Tina has already performed SCD fitting with Cigar and presented the result just before my talk. The purpose of this work is to compare the physical properties between Akari source with HSC counterpart and those without HSC counterpart. So I adapted an exactly same parameter set what Tina used on this blue circle, where we assumed following star formation history, single stellar population, dust attenuation law, agent emission, and dust emission. One major difference from Tina is that I also parameterized redshift, this red circle one. So, which means that Shigao tried to determine photometric redshift and physical properties simultaneously in this work. This is an example of the SCD fitting with Shigao. Black points are our dataset, and as you can see, most of them are upper limit, 3 sigma upper limit. And blue, yellow, and red line are stellar and AGN, and also star formation component. As you can see, our data points are moderately well fitted by Shigao, I believe. So let's go ahead, next step. From now on, let me discuss physical properties derived by Shigao and compare the result between Tina's sample and our sample. This figure shows the infrared luminosity contributed to AGN, let's say AGN luminosity as a function of redshift. And blue and yellow points are Akari source with HSC counterpart. And yellow one have photometric redshift, and blue one have spectroscopic redshift. And red points are our sample, Akari sources without HSC counterpart. As you can see, our sample has larger AGN luminosity compared with Tina's sample, Akari with HSC counterpart. This is also simply because I guess our object is also located at higher redshift than Tina's sample. So how about AGN fraction? This figure shows a histogram of AGN fraction for Akari sources with HSC counterpart and also those without HSC counterpart. As you can see, our sample, Akari source without HSC counterpart has larger AGN fraction compared with Tina's sample, which means that Akari sources without HSC counterpart may be AGN dominant population basically. How about the dust attenuation? This figure again histogram of dust attenuation at ultraviolet. As you can see, this red one, our sample, you can see the clear offset. Our sample is more affected by dust extinction compared with Tina's sample. Alright, so let me summarize what we learned from the SCD fitting. By performing the SCD fitting with Shigao and comparing the result between Akari sources with HSC counterpart and Akari sources without HSC counterpart, we found that Akari sources without HSC counterpart has larger AGN luminosity and higher redshift, and also higher AGN fraction, and also a large dust attenuation compared with Tina's sample. So this result could suggest that Akari sources without HSC counterpart may be extremely dusty obscure AGNs at redshift around 1 to 4. So finally, let me briefly discuss how many Akari sources without HSC counterpart would be detectable by Scuba 2. So far, roughly 12 objects are located that covered by Scuba 2 data, but Scuba 2 follow-up observation is ongoing. So let me estimate how many sources are eventually detected by Scuba 2. Again, this figure shows an example of the SCD. Actually, this vertical orange line represents the observed frame Scuba 2 850 micron. So if we believe the best fit SCD, or given the best fit SCD, we can estimate the expected flux density at 850 micron. And here is an example of the expected flux density at 850 micron, but x-axis is actually a log scale. So if we, I'm not sure, but detection limit of scuba 2 is, for example, 1 meter Jansky, roughly 10 objects would be eventually detectable by scuba 2 850 micron. Alright, let me summarize my talk. In my talk, I basically have 4 take-home messages. First one is we successfully discovered 139 Akari sources without HSC counterpart. Also, their spectral color is systematically redder than that of HSC Akari sources. By performing the SCD fitting and comparing the result between our sample and Tina's sample, Akari sources without HSC counterpart has larger agent luminosity at high redshift, and also higher agent fraction, and also heavier dust attenuation. My most important message in my talk is that we may discover extremely dust-obscured AGNs at redshift around 1 to 4. Alright, that's it. Thank you for your kind attention.
So, questions?
It's very, very interesting work. So, what's the AGN volumetric luminosity, and then how does it compare to the AGN luminosity function?
It's at the top end, 10 to the 12 suns.
Okay.
Yeah. So, well, actually, not top end. That would only be less than 10 to the 46, but it's that makes it more powerful than 3C273.
But then, is the number density consistent with what we know?
I have not yet checked. Yeah, but it's a good point. Yeah, we have to check number density are consistent.
Yeah, because you only searched 1 square degree or less to find these.
This one's we use always NAP.
5 square degree?
Yes.
Yeah. Okay.
But then 100 over 100, right?
Right.
Well, I don't know. It's not completely obvious whether it's going to work out or not.
Yes.
Compared to known luminous quasars at
Right.
redshift of 3. Let's
Need to
check.
try to estimate the ratio of luminous to infrared quasars in such a case.
Not yet. Yeah, but it should be. That should be done.
So it's a long shot, but anything we can get at other wavelengths. Does Sigale predict a detectable radio flux? At all?
Right. I estimate at least scuba to 850.
Yeah. But at longer wavelengths, it's too faint?
I'm not sure. Unfortunately, this our field was not covered by ALMA, so maybe we have to propose, for example, Noema or something like that, if we want to follow up with the data.
Sigala will not predict anything for quasars in range.
Okay.
Stuff for galaxy yet, not
Yes.
idea. You don't rate how it is reading voice.
Well, okay, the AGN might be several times higher in the radio than what the star-firm ratio
so
would
it's
be.
not possible to predict.
I just made a
Does it make
prediction,
sense to use some other AGN figure to try to predict the radio flux?
Well, yeah, so I'll look at it, but I suspect the radio data we have is not deep enough, but we should.
Yeah, we can check that.
You didn't check.
So there are
Yeah,
so
please
there
go
are
on.
no automatic data physical using two parts, which means so how reliable the physical parameters derived from Sigala, especially for the dust obscuration or the stellar mass or the things.
Yeah, that's a very good
The
point.
upper limits are
Yeah.
pretty powerful.
Where is that? Anyway, this is an example of the images.
Looks pretty good.
Yes. So yes, as you know, Shiga outputs a probability distribution function for parameters. For example, what's this? This is attenuation. Yeah, some of them are, you can see the very single peak, it's okay. But worst case, there are several sub-peaks. In that case, these objects are quite hard to determine their reliable dust attenuation. But anyway, we can check this kind of probability distribution function, and then how reliable Shiga can estimate parameters.
The point is, for even for good case, because there is no constraint, which means that we cannot trust the PDF, right? So probably one task we can do is we can play with galaxies with full alternative data and remove UV and optical part to see how the physical parameters are different from the case that you got. Right? It would be a useful test.
All right.
What is the redshift range that the sampling redshift that you gave at the beginning?
Redshift range?
Yeah. So the sampling, is it 4, 5, 6, 7? No, well, you can think that it's the envelope that you get for the PDF, but the single peaks.
So this is just automatically.
If you increase the sampling, maybe you will get something.
Okay.
If I remember correctly, I think that Tina's sample was our partial detected. So I'm not sure that it is fair to compare your result with Tina's result.
Right. You know, our sample are not always detected by Herschel. Yeah. At least we can put upper limit, but I'm not sure upper limit of far infrared band are reliable to estimate reliable physical quantities.
I have a quick question. Do you have a pure star-forming galaxy in your sample? No AGN?
A few sources with AGN fraction is less than, let's say, 0.1 or something. But a very minority, yeah.
Okay, so they would be candidates for dusty star-forming galaxies?
Yes, very few sources, yeah. But majority is dusty obscure AGNs, not starburst.
Only the majority is AGN this time, because only the dust extinction determines the non-detection of HSC value. So why?
Yes, that's point, yeah. For example, SMGs are very starburst galaxies that hide the universe. So I originally expect some of them are very starburst galaxies that hide less shift. But eventually, our sources are basically AGN dominant sources. Yeah. I'm still not sure how to figure out why is that.
How about stacking non-detector bands?
Yeah, that's a good idea. Yeah.